much for joining. Welcome to our webinar, Merging Power System and Power Electronics for Smart Grids with SIMBA, Python, and Julia. I'm Frédéric Peyret, Head of Marketing here at PowerSys, and I will be your host. Our today's webinar has been done in collaboration with the University of Vaasa in Finland. And today, we are excited to have with us 3 speakers. Let me introduce them. So first of all, Professor Marcelo Godoy Simoes. Hello, Marcelo.
Hello, I'm here. Good morning.
Marcelo is professor in flexible and smart power system at the University of Vaasa. He developed several AI-based power electronics for renewable energy and smart grid integration with several advanced applications, such as wind energy conversion and early automation control-based model of fuel cells. His current research interests include smart grid-based inverters for renewable energy, power electronics and power systems, power quality, renewable energy, artificial intelligence. We also have with us Peyman Razmi. Hello, Peyman.
Hello.
Peyman, morning. Peyman is a PhD scholar in power electronics, proficient in programming languages including Python, Java, Julia. Peyman combines his expertise in power electronics with advanced data science and AI techniques. And finally, we have also Luca Ferranti with us. Hello, Luca.
Hello.
Luca is a doctoral researcher at the University of Vaasa as well. His research interests lie in scientific computing, computer algebra, automated reasoning, fuzzy logic, and their application. And Luca is a Julia enthusiast and has developed research software in Julia and worked as Julia software engineer. Over the next hour, we will explain how to make your smart grid smarter, more flexible, and efficient. So let me share with you the agenda of our presentation today. Professor Simoes will discuss unified modeling and simulation analysis of power electronics, power system, and smart grids. In the second part, Peyman will present a Python and SIMBA simulation case study. And to complete this webinar, Luca will go through a live Pluto notebook software-based presentation of Julia for electrical engineering systems. We will then have our Q&A session. So don't forget to ask your question in the chat box. And then we will end our webinar by some announcement and conclusion. Before we get started, there are a couple of things I need to tell you. First of all, any of the speakers or I are happy to answer your questions. So again, don't forget to ask your question even during the presentation in the chat box. During the webinar, we will also conduct a series of quick polls to gather your immediate feedback. So don't hesitate to participate. Your input is really invaluable to us. And lastly, if you have time at the end of the webinar, we will send you a small survey to answer. So please feel free to fill this questionnaire so that we can improve things in the future for you. Now, let me quickly introduce you PowerSys and why we partnered with the University of Vaasa for this webinar. At PowerSys, we are experts in model-based design simulation software and electrification since 2002. We help the industries to accelerate their electrification by decreasing the time to market. For that, we provide electromagnetics and power electronics simulation toolchain and power computing that will allow companies to optimize their electric design for performance and manufacturability. So if you want more information, I will put in the chat my contact details. Feel free to contact me. In our today webinar, you will see how Marcelo and his team used our power electronic simulation tool, SIMBA, to merge power system and power electronics for smart grid. Now, if everyone is ready, let's get started. Marcelo, the floor is yours.
Thank you very much. Just switching here to my screen. Okay, so I hope everyone hears me because now I just see the screen of my computer.
It's okay.
And thank you. I will start with some initial ideas. My intention right now at this section is to give you what I believe should be a comprehensive approach to model power electronics with power systems and smart grid in a unified, how to say, formulation. Because when I was a student, I remember well that we were compartmentalized, and people who knew power electronics were one group, power systems another one, control systems another one. Computer science was just emerging when I was kind of a student a long time ago. But nowadays, if you want to make an impact, and if you really want to contribute to our society, you have to master this in a comprehensive way. So those are my initial ideas. When we start to learn and understand power electronics and power systems, we go by models. We have to have models typically based on physics or chemistry or science. And electrical engineering is very much attached to understanding physics and mathematics in a way that everything makes sense. So this has been for many years the traditional way that we teach, model, and analyze a transmission distribution power systems. We make the assumption that we have a bulk power system, and we have the distribution system here. So the generation will have the voltage being raised, will be transported for many kilometers or miles in a high voltage, then we step down in a substation, and then distribution and users. So when we start to model here, we usually go to the section that we want to model, and we can try to forget what else is connected to that point. So, and we also try to imagine that the electrical energy will travel just one way. So this has been for many decades the way that we learn how to model these kind of systems, and we make simplified models. Could be power systems, power electronics, but that's the way, okay? So in the past, you can see here that the power grid was very simple. Okay, so this was what, 50, 60 years ago, where large power plants would raise the voltage to a substation, and then a system operator would just use a phone to talk to the ends, of the substations here, and see what's the requirement for the next 6 hours or so. Okay, so that was a simple phone call 50 years ago. And then the power station here would program their capability to supply power to industrial customers, commercial customers, and residential customers. We have been moving on the past maybe 20, 25 years to what we call present. And the present has a little bit also of the future. So let's see what would be a present that's very typical in most of the countries. We have more controls with computers. We call this system of supervisory control here at the transmission distribution level is SCADA. Okay, it's a supervisory control system with PLCs, computers. So we have automation, and the transmission is kind of well organized because it's big money that the utilities will be in charge of. Okay, so eventually it was, how to say, common that the automation started where the how to say, the resources were more concentrated on large power instead of the small power. Okay, so you see here that we may have some injection of renewable energy, big wind farms or in power plants or solar power, typically at the transmission, sub-transmission level. And we would assume that for these present days, the power flows still, to these customers, and there is a bidirectional power and some communication here on the high voltage level, but we didn't reach yet with this formulation total implementation of smart grids. What we have now, when I say future, that also means that some of this is available right now. Okay, it's the future from now on. So from now on, we expect way more communication protocols and interaction of data and electricity. So the black lines here, they would show how electricity is flowing. The dashed blue lines here would be sorts of all types of communications. And you see here that we have more integration. We have here a smart grid connecting other points or using wind farms or solar arrays. And also now we have this flexibility of having electric vehicles, electric cars. An electric car will have 80 kilowatts, 100 kilowatts. So you are driving a small power plant. Okay, when you hop in your car and you drive from point A to point B, you are taking your power plant with you. So when you connect again in your destination, you can recharge your battery or you can even sell power. Okay, so this flexibility makes electric vehicles something that must be also adopted in this formulation of smart grids. In addition, we want to move away from fossil fuel. Okay, so the society of the future, if it's a fair and sustainable society, should diminish, and possibly zero if it's possible, to use fossil fuel and adopt renewable energy solutions. So that's the future, and that's what we are aiming for our future generation. So the power systems, electricity, they were very simple in the last 100 years. The grid was designed to be unidirectional, and smart grid could be defined in several ways. The way that I like to say in a conversation or even in a lecture in a class is smart grid. You can imagine that's a dialogue. It's a two-way dialogue of electricity and information. Electricity and information are exchanged and traveling between the customers and the utility. And how this dialogue is implemented is the implementation of a smart grid. So we need a network of communications, controls, computers, automations, new technology, new tools. We want to have a green system. We want to have an efficient system. We want to have technology that will integrate wind and solar energy, plug-in electric cars. So the smart grid is the new infrastructure of what is today's grid. For that, we have to have controls and real-time systems. I could digress now, but we don't have time because this is a webinar, but I could digress now, for example, to what happened to the ship that collided in that bridge in the United States. So what does that have to do with the discussion here? Because the idea is that we have to have real-time control systems that are fault tolerant. When we have a fault, when you have a problem, the system must be safe and we have to preserve lives, okay? So an engineer has to have that in their design. So we have to train the new generation of students, engineers, and professionals. So my proposal is that power electronics, with all the competences and all needs that we know, and power systems with all core competences of electrical circuit theory, power flow, and so on, they are merged on this approach of smart grid. So a smart grid is this overlap of skills, competence, and understanding in a comprehensive way. This would be how electrical circuits could be modeled and analyzed, and that depends on the implementation. That depends if you have slow dynamics or fast dynamics. We don't have time to go through this in this webinar, but you see here that I have several sets of events with different bandwidth and different dynamics, and they should be implemented in the order of microseconds or milliseconds or seconds or minutes or hours or days or even months, depending what you're doing. And we have to have an understanding and a comprehensive way to do that. So that's the beauty of adopting SIMBA, for example, the software that we use for these case studies, and why we decided that Python and Julia would be important add-ons for SIMBA. We have in our society several technical groups like IEEE and SIGRI, and they discuss transient stability and how would be electromagnetic models and simulation tools. And PowerSys is a key player in this. They have solutions, they have invested in software, they have people with credentials to support these EMT discussions. When we want to go to the real life for really modeling and electrical power systems, we have several approaches. So here I try to give you a perspective. You may have time domain analysis. You may have state space averaging when we want to simplify our model in a way that you can implement that you are not interested maybe in the switching of your transistors, let's say. So there are several techniques that we can use to understand the electrical engineering systems with solutions that will require a correct understanding in how analysis and simulation should be done. And this is also related with the real-time control, and if we are doing this for fast dynamics or slow dynamics. And then we have the discussion of computational power. So what kind of computer do I use? For how many microseconds I have to design my control systems? Is my computer tabletop personal computer, or it's on the cloud, or it's DSP, embedded hardware control, or FPGA? So depending what you're doing, you have to understand the simulation speed, the execution speed, and how you can deal with a diversity of applications in the electrical engineering. Here we also discuss on this slide how electrical circuits analysis, model and control could be approach for your transient analysis. And as I have been discussing, that would be the idea of fast versus slow dynamics. If you are doing transient control, fast dynamic simulation, power energy management, maybe a study on stability, maybe scheduling of energy, maybe a long-term planning, okay? So when we use hardware in the loop, there are so many options, okay? Here we have a very strong key player on this area that we adopt here as well. So I have experience with many implementations of hardware in the loop with many other manufacturers and many other solutions. And in this webinar, we decide to bring you a case study of SIMBA and Python that will be presented by Payman, and how we can use Julia for power system simulations and also artificial intelligence, because we believe this will help us to move along, and we want to motivate you to work on that. We want you to be able to validate your controller, to test your inverter responses with scenarios, to maybe fine-tune your control systems, to study power quality computation, the time, everything that's required to make sure that your system is working properly. And pay attention, you have to always make your responsibility that whatever you design has safety in consideration. It's a safe mode control to avoid catastrophic happenings as it happened these days with that ship. Okay? So the best environment that makes you to work, even though we have so many frameworks, MATLAB, Simulink, PSYN, Plex, RTDS, PSCAD, DigiSilent, Modelica, JMag, ANSYS, Simplora, SIMBA, of course. But the best environment is that allows an interdisciplinary team to cooperate and to help you to make the best design. So now, before I move, we have to have a quick survey. So I will ask Frederick to put a survey here. So you see here questions. Would you favor a feedback or a feed-forward control approach in power electronics and power systems? What do you believe? Would be more motivated to use a feedback control or a feed-forward control? Do you understand what's feedback or feed-forward? Just put your choice, and we can see your answers and make a little bit of comment before I continue the rest of this section. Thank you.
The answers are coming. Yeah. Ten seconds and it will be over. Marcelo, I share the results.
Okay, you can share the results. I'd like to see the percentage of the response.
We have 72% for feedback and 28% for feed-forward.
Great. Okay. Thanks. So this shows one thing. Most of you, most of us, we are used to the idea of feedback. Feedback is very important. Okay. I just wrote an article for the IEEE Electrification magazine discussing how feedback became to be one of the most important issues in engineering and electrical engineering. So I recommend you to take a look on that. Some people decide on feed forward, maybe because these people who knows what feed forward, they know that typically when you have a feed forward, you make a physics-based modeling and you try to counter-react things that happens. For example, if you go to the moon, typically it's feed forward. You make calculations, but you just correct on the way. There is no feedback loop control that will really make the spaceship to arrive to the moon. Okay, it's not a real-time control. However, that capsule will have some real-time control itself. Okay, so the idea of feedback and feed-forward is very important for the realization of control systems. Okay, so coming back, we could move along with this, but coming back, when we want to understand our world, we make an observation and we take data analysis and we have a decision making. So the real world will have a model, and that model is somehow implemented in a system that could be an equation or could be maybe AI. Okay. So I'm bringing back here this observation of Professor Zadeh, Lotfi Zadeh, who was the father of fuzzy logic. That was a very interesting, how to say, motivation to what's happening today. where when we observe the real world and you try to make a model for decision making and you try to bring more math and physics, as complexity rises, precise statements lose meaning and meaningful statements lose precision. Okay, so he was in favor of the idea of computing with words, description using ad hoc observations of the world. Okay, that's the way that fuzzy logic was born. Okay, industrial systems could be modeled for condition monitoring, fault detection, diagnosis. We have to have sensor validation. So there are several techniques that we can use for implementing fuzzy logic and neural networks. They have here some of the following features. So this is in my notes, in my books, in my classes, and I will be happy to entertain discussions maybe in another time. And artificial neural networks could be useful for many applications here: pattern recognition, associative memory, optimization, functional approximation, modeling control, image processing, classification, clustering. And here you see what type of artificial neural network would be, how to say, a very good solution for that particular problem. And then in the activity that we try to implement AI, artificial intelligence, and machine learning into power systems, could be for prediction, classification, data association, data conceptualization, data filtering. So here we see some kind of neural network topologies and the application. Okay. And we also have to consider here that power systems, to be smarter, they have to have an approach that will allow to consider several of the, how to say, constraints and requirements of those power electronics and power systems. Maybe parameter variations, maybe you have process that you can model in a verbal way, but you don't have a mathematical model. Maybe you try to use a PI or PID control, but you cannot all the time attend to the control requirements that you need. So the idea that we should have a technique that would allow the implementation of neural networks in fuzzy logic, it's a very important one. Okay. So going along on this, we talk usually about deep learning, and everybody likes to mention about deep learning. What I tell in my classes, in my lectures, is that deep learning is a neural network. Deep learning is neural network on steroids, I would say. Okay, there is a historical description of how cybernetics became a wave of neural networks. And then there was a kind of death of neural networks at the beginning of the 70s, 1970s. And then there was a resurgence of neural networks at the middle of the 80s with backpropagation. And then during the first decade of 21st century, about 2007, 2008, there was a saturation of utilization of neural networks, and there was a reason for that. And the reason was that with very complex problems with huge data, they could not have convergence of the neural networks. So deep learning came in 2011, 2012 to fix that, okay? But now they replace. Now everybody talks about deep learning, but they forgot that deep learning is actually a neural network, okay? So if you want to learn deep learning, you have to start learning neural networks. And nowadays, we have this need and this increasing penetration of solar and wind power in the electricity grid with bidirectional power, prosumers, integrated communication, and we need some and further scheduling and operation of smart power systems. They are compromised with challenges of uncertainty, generation, and mobile flexible loads. And we need to have forecasting of energy demands at different layers in this integrated power system, okay? So we also have to consider how future smart meters and cognitive will provide an opportunity for data that will be used for these deep learning algorithms. Here again, we are coming back to machine learning, supervised and unsupervised learning, and some classifications of artificial neural network-based power systems, how we can use that to advance the design, modeling, and simulation of these systems. These would be some future applications for AI, power electronics and power systems, for smart grids, sustainable renewable energy, electric and plug-in cars. In addition to being a transportation solution, an electric car is a portable power and storage plant. So maybe artificial intelligence would allow, I don't know, capabilities on the car like torque estimation, safety, driverless control. There is how to say a very vast and very exciting area coming ahead of us that we have to be prepared. So my recommendation for everyone is try your best to understand the requirements for smart grid systems and deep learning, how we can use AI for smarter power systems. For example, this is a simulation I made some time ago using EMPHAS for a wind farm, how we could use signals of this wind farm to check on the conditions of how the wind farm is operating. Also, something important is to understand how to implement systems that are modeled in real time and they have forecasting. So coming back to the spacecraft industry, we imported their approach called digital twin. When an aircraft is flying, we do not have access to that anymore, used in the past, okay? So the only thing you could do is to model what's happening with that aircraft in our control systems and try to communicate with the pilot. Okay, so the digital twin started in the 70s and the 80s on the aircraft industry, and now it's something that's adopted by power systems and power electronics. So I would suggest you to also understand how to implement virtual model-based real-time systems. They are called digital twins. So some announcements here about our workshop. Maybe I will pass this a little bit to Frederick, and then she can give the floor to the next speaker. So Frederick, would you like to say anything about the involvement power systems and about the workshop that we're organizing here in University of Vaasa? And then you can give the floor to Penguin.
Sure. Sure, Marcelo. Yes, just some indeed announcement about some future events where PowerSys and the University of Vaasa will be. So we will exhibit at PCIM in June, just for info. And the University of Vaasa will organize a workshop on artificial intelligence and machine learning for energy transformation. And I think that Luca is going maybe to give some insight in his presentation. So without further ado, I leave the speakerphone, I would say, to Payman.
Okay, we stop sharing and I will ask Payman to take over. Thank you very much.
Hello, everyone. Hope you're fine. Welcome to our session on SIMBA software introduction. My name is Peyman Razmi, PhD researcher in power system and power electronics. Today, we will reveal the essential of SIMBA and how we can harness the power of the Python programming within SIMBA simulation environments. Also, we will learn how these tools, Python, SIMBA, and also Julia, come together to streamline and empower your simulation project. Today, in this session, I will talk about introduction of Python programming, Python environments and libraries, introduction to a SIMBA environment and its capabilities, power converter simulation in SIMBA, and also management of SIMBA simulation with Python. And also, if times allow, I will briefly make a reference to essential Julia libraries employed in SIMBA. As we know, Python is popular high-level programming languages used in various applications. It is an easy language to learn because of its simple syntax. And also, it can be used for simple tasks, from plotting projects and also for very complex projects like algebra programming, optimization, and also machine learning algorithms. Unlike some language like Java, Python doesn't require a compilation step. In Java, you write your code, which is then compiled with bytecode. And then this bytecode is what runs on the Java virtual machine. In contrast, Python is directly interpreted. You write your code in PyPy and then it's run directly by Python interpreter. This means you can run your codes without any intermediate compilation step. It's like having a conservation in real time with computer where Python translates your instructions on the fly. Here, there is three fundamental elements that construct the core of the Python programming code, includes variable, objects, and classes. In the first step and the main core of structure, we have variables. In Python, variable can store data, any type, like numbers, string, list, boolean, and so on. In the middle layer, we have objects. An object is a collection of data and represent the complete information of entity. In upper level, we have classes. A class is a collection of objects and acts as a template for objects, defining their features and actions with methods. These methods also are functions defined in the classes, which maybe for some calculation inside the classes. These features like variables, objects, and classes can construct a part of libraries. And also, I will talk about libraries and how can these libraries can be beneficial in our Python and also SIMBA project. In Python, we have a lot of libraries. In scientific computing, we have NumPy, Panda, SciPy, and Matplotlib, and also machine learning algorithms like scikit-learn, TensorFlow, Keras, and also PyTorch. I will talk about these libraries in Python and also connection with a SIMBA project. SIMBA is a software platform used for simulating power converters and also motor drives. It provides tools and also features for modeling and analyzing electrical systems and components, allowing us to simulate the system behavior. This page is the main page of the SIMBA after installing the software. And also, as you can see, we have 4 buttons. In the new project, you can start a new SIMBA project. In open project, you can open your local SIMBA projects. In design examples, you can see all collection of design example, and in Get Start, you can learn more about essential features of SIMBA. So let's go to SIMBA environment. In this new project, as you can see, we have several menu bars, design menu bars, libraries, test bench, design, and also results. In design menu bar, you can create your own simulation here. And also if you have several these simulation in one project, you can add here and also design its names. This name is so important in Python projects if connected to Python. In libraries, you can see a lot of components: electrical, mechanical, thermal, control, and other components. In electrical, you can find several elements like transformers, switches, source, semiconductors, probes, motors, and also RLC impedance. Test bench includes various parameter analysis and very good options for parameter sweep analysis. And also design, you can see your simulation page. And final, you can see our simulation results after running. But before running, you should set solver type here, mean time steps, and also end time. Now we are going to start to simulate a simple buck boost converter and evaluate the results in SIMBA environment and Python separately. So as you can see, we need elements like DC source, PWM pulse generator, MOSFETs, inductor, diode, capacitor, and also resistance. So let's go to SIMBA. We got these elements from libraries. Only needs to connect together and finally set values. For voltage DC source, we consider 8-volt. Inductor, we consider 10 microhenry. For capacitor, 10 microfarad. And also for loads, 10 ohm. In this section, there is scope section, like here, voltage scopes and so current scopes for each elements. And also by activating these sections, you can see waveform for each elements. Here, because we need to see output voltage across loads, we should activate this one, current and also voltage scopes. And also here, we should set PWM parameters and duty cycle of 0.8 for the duty cycle and also frequency 5,000 kilo. But after running, we should set here. This means time step and also end time. And then we can short run here to see results. This is output, voltage output, and also here current output across loads and resistors. By using this one export, we can save output voltage and also output currents in the form of PNG and also CSV file. We can also do the same procedure and also get these outputs from Python. Only needs to call this simulation by calling this project name and also design name. You can rename here and change the design names. So let's go to Python codes. Here you can see the Python codes for calling simulation and also analyzing. Here we call and also import essential libraries like import matplotlib, pyplat for plotting. Here we need to import JSON project repository from SIMBA because our simulation is stored as a JSON data. And finally, in here, import operating system for management files and folders. In this section, we need to call simulation by calling project name here and also design name here. This section solves the system in transient mode. And finally here, calculation voltage output across here resistance. And here we should get output voltage and waveform here. And then run. As you can see, the results are the same we got in SIMBA environment. Okay. And now we want to analyze the parameter sweep in SIMBA. One of the important benefits of SIMBA is being easy to use the parameter sweep analysis. In parameter sweep problem, we change the parameters and study the system behavior. Here in a buck-boost converter, we change the loads from 1 to 300 ohm and see how the system behavior changes from CCM mode to DCM mode. So we need only to monitor inductor current with load changing. As we know, in power converter, when inductor current reach to 0, it means reach to DCM modes, and it caused by high-level loads. So we can do these tasks also in from Python and also in SIMBA environment. Let's go to SIMBA. In test bench, here in parameter sweep section, we need to assign design name here, device that can be changed, loads, and also here 300 ohm with 15 steps.
I'm not hearing payment. I don't know if your mic is blocked.
Payman,
I
can you
cannot
hear
hear
us?
the
Okay. Now we can hear you.
Yes. It's running to get simulation results now in this section. It takes a little time to get results because I select 15 steps here to get visible output. Now you can see the output. In parameter sweep. Not current. As you can see here, for loads more than 100 ohm, system goes to DCM mode. We can also do this procedure in Python, only needs to create a loop for resistance. So come back to Python codes. As you can see here, I put my code and in the section import multiplet.pyplat libraries as the same before a JSON project for import or simulation, import OS, and also import NumPy. This section, we also call our simulation project. This section, we create a loop for load from 100 to 300 ohm. This section we set load values inside loop, and also this section solve in system is in transit mode and run calculation. And also here we get inductor current. Finally, we solve the problem and draw waveform plotting. After running this simulation, it takes a little time to get result. maybe the problem and start and also run again. It takes time because I choose steps for running time.
Payman, do you have the result to show us? Maybe on a slide or something like that?
Yes. But now maybe we got results.
Okay.
We can go on with other slides and to wait to get results. In Julia, as my colleague will explain in the next section, we can also perform this same procedure we had in Python. First, we need to import Julia libraries, PyCal and also PyPlat. Then import Python libraries by using PyImport. And other instructions are similar to Python codes. So let's go to Julia code. Here you can see Julia code. Here we import Julia libraries, PyCal and PyPlat. This section we need to import Python libraries in Julia. This section calling the simulation from SIMBA, and this section solve the system in transit mode. And here we calculate output voltage across resistance and then plotting. So we need to run these codes. As you can see, the results are the same we got in Python before. And also in Python, we got the same results we got in SIMBA in test bench section. Here I finished, and also I simulated my tasks presentation here, and invite the Luca to explain more on Julia. Thank you very much. Thank you.
Thank you, Payman. Luca, it's up to you now.
Hello, everyone. Payman, can you stop sharing so that I can share?
I'm sorry, Luca. Are you going to have a poll? Another survey?
Yeah, I'm going to have a poll soon. Actually, Frederick.
We should have a poll from after payment. There was one after him, just to be
sorry.
completed.
Yes,
Yeah.
indeed, Marcelo, thank you very much.
Thank you.
we just showed the question, is Python a good tool to support your power electronic simulation analysis? I'll let you 20 seconds more to answer, as I would like Luca to do his part and not exceeding too much the hour.
And Payman, can you stop screen sharing so I can share my screen?
And this is the end. Thank you very much. I will end the poll. So 85% of the respondents said that yes, Python is a good tool to support the power electronic simulation analysis. Thank you very much, guys. Luca, it's up to you now.
Yeah, except it isn't because I cannot screen share if Payman is still screen sharing. So can someone stop his screen share?
Payman, can you stop sharing your screen so Luca can go next?
Yes, yes.
You're still screen sharing. Thank you. Okay, can you see my slides?
Yes.
Should see Julia overview, Luca Ferranti, cool. Hello everyone, I'm Luca and I will talk about Julia, these very cool languages I'm very excited about. But first, let's take a quick poll because I would like to hear what programming languages you have heard, worked on. So Frederick, if you could start the poll. Yeah, so we have a few multiple choice questions like what programming languages you have used for simulation, Julia, Python, C, C++, Fortran, MATLAB, none. Okay, that's interesting option. And if you have used something else, you can write in the text field. Yeah, and maybe while people answer the question, I can introduce myself briefly. So I'm Luca Ferranti indeed. I also work at the university as PhD student and also work as a Julia software engineer. I'm very passionate about Julia, about open source, and among other things, I organized the Julia Users Helsinki, this meetup, informal meetup for Julia enthusiasts in Helsinki area. So if you like Julia and are in Helsinki area, we meet once a month. So hope to see someone if you pass by Finland. Are we done with the poll, Frederick? Can we?
Almost second, and it's done.
Okay.
So you should see now the results. I would say it's quite 86% mentioned MATLAB. So you know.
Okay, cool. So very
we have several answers. So
yeah. So I'm not surprised actually, and of this because MATLAB is in a way like. So I'll go in a second why I'm not surprised. But first, I'm very sorry, Frederick, for the next slide. I just couldn't resist. So some people may wonder, where is SIMBA in this presentation? So here it is. So I will not talk too much about the existing integration, but give an overview about the Julia features and why Julia is cool. And then if there's more interest, we can chat offload and maybe from also SIMBA team, if people are interested in make Julia SIMBA integration more strong, we can discuss how to make it happen. But with no further, let's go into what is Julia. So Julia is a programming language developed at MIT a little over 10 years ago. And it's open source, so it's free as in free beer for everyone. It has a thriving community and a very rich ecosystem. And Julia was developed from researchers for researchers. So the goal of Julia is to make scientific computing and modeling as easy and engaging as possible. And particularly, Julia aims at solving the so-called two languages problem. So we heard also from Payman presentation that we have like Python or MATLAB, which are like dynamic languages. So they're interactive. You can try things on a REPL on an interactive session, which is very good for research, for development. Because when we do research, we generally, don't know what we are doing. We try stuff when we need to design a system. We need to try different parameters, to try different things. So we need interactivity for designing, for planning. But then once we have our champion model, we have optimized all the parameters, optimized all the architecture, blah, blah, blah. We realize, oh, crap, Python is slow. We need fast code. And so we needed to rewrite everything in C or C++ or Fortran or whatever. And this is called the two languages problem, where you need to choose between being fast or being expressive, being fast or being good for prototyping. So you need one language to prototype and one language to develop. What Julia says, why not both? I want both. So Julia wants to offer one language where it's easy to prototype without giving up on speed. So Julia is dynamic by definition. It's a dynamic language. So you have a REPL interactive session, just like Python. You can use in Jupyter Notebook. Actually, Julia is the JU in Jupyter. So it's interactive, but then it's also fast. So this is one of the key points of Julia. Dynamic, but still fast. And other features I want to highlight, Julia is also expressive, very, very important for prototyping, for research, for development, because you want to communicate your results. You don't want to have some unreadable C code to give your colleagues. So very important, and also composable. I'll talk about that later. But let's start with the first feature. So Julia is fast. And here you have some benchmark from the Julia people, which shows a surprise, that Julia achieves like a C performance. And now you say, yeah, whatever. But of course, like a benchmark done by Julia developers shows that Julia is fast. That's just how marketing works. Like I sell you my product, I show that my product is good. Okay, don't listen to Julia people. Fair enough. This is a Twitter from Chapel people, completely different programming languages from completely different company. And what they do here in this graph, they have runtime, so how fast the language is, and compressed code size, so like how long it was to write the code, how long the source code was. And if you look at most languages, they either are like expressive but slow, or fast but like very difficult to write. Whereas Julia and, well, Chapel, since it's from Chapel people, are this like in this unique corner where they are fast, but still very expressive, very short to write. And how is, I'm sharing the slides. The slides are on my website, actually. So yeah, I see this question 20 times in the FAQ. Yeah, my slides will be public. How does Julia achieve this speed? The killer feature, and don't worry, I will not get into implementation details or technical details. I can give more pointers, but I want to give like idea. Where does the speed come from? The key secret feature is this feature called multiple dispatch. So multiple dispatch is how Julia allows to be fast while still being dynamic. And I'll give like very, very, very simple overview of multiple dispatch. Like, why does it make it possible? So dynamic language, it means that we check things at runtime when we run a code, whereas in C code, compiled language, you can, you know everything ahead of time, so you can do optimization. What Julia does has multiple dispatch and also has a feature called the type inference, which means that it's dynamic, but if you write a so-called stable code so that the compiler happens to know all the types of everything, it can do optimization, and it almost magically becomes a static language, like static language. So it's dynamic, but if you write code in the good way, it achieves the speed of a static language because it behaves like static language. And yeah, this is very short example to multiple dispatch that if you want to write like a rock, paper, scissors game in Julia, or the better rock, paper, scissors, lizard, Spock version, you would do it this way, but I'll skip this for time. I want to give a further motivation for multiple dispatch and why Julia is good. Probably all of you know about LAPACK, and if you don't know about LAPACK, you're actually dependent on LAPACK without knowing it. So LAPACK is this huge library of linear algebra routines for eigenvalues, for linear systems, matrix multiplications, and so on and so on and so on. And everyone uses it. And if you look like at the original LAPACK paper, so like from I don't know what decades, but it's pretty old. The LAPACK authors, Jack Dongara, who won the Turing Award recently, and Demel, who I think also won at some point, they say, why is linear algebra hard? Because what do you want to do in linear algebra? So for all possible problems, like linear systems problem, eigenvalue problem, QR decomposition problem, and so on, for all type of matrices, because you have matrices with no structure, you have brute force algorithm, but then you can have symmetric matrices, which have like more properties and more structure, so more optimized algorithms. So all matrices, all problems, all data types, because you can have matrices of in single precision, in double precision, you can have complex numbers, matrix of complex numbers, and you don't want to use the same algorithm because algorithms for real matrices are faster algorithms for complex matrices. and so on and so on. So for all these huge tensor product of combination, you need to choose, you need to have a different algorithm, because algorithms for generic algorithm for complex matrices are not optimal for real matrices. And algorithm for generic real matrices are not optimal for diagonal or symmetric matrices. And what LAPACK does indeed has like a huge collection of functions. And this makes like the code hard to write, hard to read, because you need to know before ahead what matrix you have and what algorithm to call. Thanks to Julia, if you want to do matrix multiplication, you can write A times B, and this is something that everyone understands. I showed this to a mathematician, understands that it's matrix multiplication. But then if your matrix is diagonal matrix, you just write A times D, but now Julia knows that this is a diagonal matrix, and hence will pick the faster algorithm for matrix multiplication between matrix and diagonal matrix. And this is the power of multiple dispatch, that this matrix multiplication has a huge number of implementations, and Julia can automatically, at compile time, pick the best one and pick the optimized one with no overhead. So you don't need to check when you run the code, is my matrix diagonal? If yes, pick that algorithm. It knows already before ahead. And this gives huge performance. Yeah, and then here I had a slide about type inference, but I'll skip this. So yeah, this is about performance. There's tons of resources about why Julia is fast. I don't even want to talk too much about that because it's the most common feature. And other features I want to talk are composability and expressiveness, which are very good for what we do, for what you do here, but maybe a little less known. So Julia is composable, which means that if I write, for example, library for differential equations, and you write library for machine learning, if you follow Julia guidelines, we can combine the two libraries together very easily with no problems. Here is a quick example where I have this library, measurements.gl, where which is a library used for like error propagation, so to have error bounds. And now what happens? I construct this object, so this A now it's kind of real number with uncertainty. And without any problem, I can automatically plot with error bars. Because, why? Because someone who implemented these implemented fulfilling like the interface of real numbers, so behaves like a real number, said how to plot this particular real number, and boom, we get automatic plotting of error bounds without an issue. Other cool thing, this object constructed with measurement is built to behave like a real number, so satisfies real number interface. Boom! You can plug it into differential equation solver, and suddenly you have uncertainty propagation through neural networks for free, just like that. Maybe not the best one because that's Taylor approximation, but whatever, it works. So you can combine packages. Thanks to Julia being so generic, so dynamic, and thanks to multiple dispatch actually. So this is possible because Julia does not use object-oriented, but multiple dispatch. It makes possible to write this generic composable code, which allows to combine libraries effortlessly. Yeah. And talking about composability, now I want to get into something which I think is going to be very interesting for you, which is the scientific machine learning ecosystem. So Julia has the strongest ecosystem for differential equations solver. And it's unfortunate some people in some slides still say Julia ecosystem is not mature, but that's just because those people are lazy and heard that 5 years ago and don't understand that things change fast. Julia ecosystem for differential equation is state of the art, has most solver than anyone else. And for example, SciPy, the Python library, now started to use Julia solvers under the hood. So Julia has a strong ecosystem for differential equations and scientific machine learning. And now I have a question for you so that you don't get asleep. And I will ask, I have a question. So Frederick, please, you can pop the next question.
Yes, I pop up the next question.
Thank you.
Is machine learning in power electronics an interesting topic for you in the near future? Talking about the subject, by the way. Let's have 5 more seconds. to collect your answers. Okay. 94% yes, Luca.
Okay. So someone thinks no anyway, or maybe didn't answer. Don't know.
Some, but few of them, only few of them.
Yeah. So if you think that machine learning is important for like simulation or power electronics, then you should definitely look into Julia, because Julia's scientific machine learning ecosystem allows combination of neural networks and differential equations, and I will show it soon. But before getting into that, I want to give like a very short overview of the scientific machine learning ecosystem and where does the power come from. So what the Julia differential equations ecosystem does, it wants to make solving differential equations as easy as possible for scientists. Like you're a scientist, you're an engineer, you understand physics, you understand power electronics, but maybe you don't know all the like nitty-gritty details of numerical methods, of numerical computations. And so maybe in other languages, like in MATLAB, in MATLAB or in C++, also in Fortran, if you have a special structure, for example, if you have a sparse problem, you need to yourself check, is my matrix sparse? Or I don't know, put a student to check, is my matrix sparse? And then if it's sparse, you need to tell the solver, hey, by the way, this matrix is sparse, so use the faster sparse solver. Or you need to try yourself based on the structure of your problem. What is the best solver? What should I use? Julia differential equations ecosystem approach is that user should get the best possible solution automatically without any like overhead. And here I have a simple example to motivate this. So suppose I want to solve this system of 5 nonlinear equations. This could be, I don't know, like, like time from solving differential equation, my nonlinear differential equation, I might end up solving this nonlinear system with a Newton method. Now, the numerical way to do it was like, okay, like I take this system, I compute the Jacobian, I do do like the Newton iteration and so on and so on. Oh, note by the way, this is how you would write it in Julia. So this is actually not LaTeX, but it's how the system is printed in this Pluto notebook. So I've read the equations like this. This is working code. I run this code. This is how you write these equations. And then you get these equations printed. So also good for expressibility and communication. But then you write the equation. And the numerical approach would be, okay, now let's compute the Jacobian, do Newton iteration, and so on and so on. But now, for example, in Julia, you can call this a structural simplify, which will say, whoa, wait a second, let me have a look at the equations. And thanks to Julia, very powerful, like computer algebra systems and like symbolic manipulations, what your the structural simplify will do is says, okay, let me see your equations. And we'll find out, whoa, you don't need to solve 5 equations. You only need to solve 1 equation. So if you start like playing with these equations, you actually find out that you have 1 equation, where U1 and U4 can be rewritten as functions of the others. And so actually, when you solve this nonlinear system, Julia will not solve a nonlinear system of 5 nonlinear equations, but will only solve 1 equation. And this will be much faster, because you say, oh yeah, of course, you solve 1 equation instead of 5. It's cheating. Yes, it's cheating because it's not solving the numerical problem. It's for you doing a better thing, solving the easier numerical problem, achieving better numerical stability, better speed. And now you tell me, yeah, but if you need to do this symbolic manipulation, then it's slower because you need to do symbolic computation. Symbolic computation is slow. Nope. Because that actually happens at compile time. So before you run your code, that's also the cool thing, that all these automatic sparsity detection and symbolic manipulation can be done before you spit the final executable of the solver. So once you have the structure of your problem fixed, all this optimization is done for you at compile time, and you get fast code. So yeah, kind of cheating because it makes life easier for you. Like in MATLAB, if you have sparse problem, you need to give the sparsity pattern. In Julia, it finds the sparsity pattern for itself, and you can solve a sparse problem without ever knowing that it was a sparse. Yep. Let me check if there are questions. Okay.
We can answer them afterwards. No worries.
Yeah. And now what I promised, like most people think that neural networks and machine learning is useful. Why is it useful for scientific computing, for modeling? Suppose we have, so this is like this, it's kind of one harmonic oscillator, and this is like the whole differential equations. So we have like the normal part here on the left, and then we have some, I don't know, like friction modeling, non-linearities, unideal things, issues, this third degree term. But now what happens? We don't know about this. This is difficult physics. We don't know it. We only know the simple equations. And then we have some measurements from experiments, from other simulations, so on. So we have simple equation, measurements, and we realize, oh no, my measurements don't match my simulation. What am I missing? And now the utility of machine learning in neural networks is that you can plug your neural network inside the differential equation and say, okay, now I have some nonlinearities, I have some non-ideal things. Let me replace that, and let me put the neural network inside my differential equation to model all these nasty nonlinearities. And you can do that because actually neural networks, it was proved by Gauss already 200 years ago, are universal approximators. So if you have good enough neural networks, you can approximate this nonlinear function. So you plug a neural network, you plug a neural network inside differential equation, pass the data to the differential equation solver, and boom, you get physics-informed neural network. So the trainer, based on the measurements, will learn the parameter of the neural networks, while also making sure that the physics, the constraint of the differential equation are satisfied. And this is much, much stronger than just giving data and training neural network. Because if you have measurements for 10 minutes and only neural networks, the second you step outside the interval time of your training data, your neural network will hallucinate, will only give a crap, because it doesn't know about the physics. While when training the neural network inside the differential equation, it also learns the physics and learns to preserve the physics. And then you get good approximation also after the time interval of the training. And how do you do in Julia? To plug a neural network into a differential equation, you literally plug a neural network inside the differential equation. Nothing more needed. So here I have simple example to solve this. So here I build, like in this case, this a type of neural network architecture to model this. Here I write my system. So this is second order differential equations. I write it as two first order equations. So this is the first equation, second equation. And now I want to point out that this part here is this part here. And then you replace the unknown with a neural network. So say, okay, now I have the linear components which I know in my differential equations. Let's add the neural network in the formulation. Then you build the OT problem, you can train it, and here you get some results. And so what happens is that the neural network, the parameters are trained to satisfy the measurements while also satisfying the physics of the differential equations. And it is very powerful in Julia because of composability. You can combine neural networks and differential equations effortlessly. Yeah. Last feature I want to very briefly, because I'm already very over time. Well, I also started when my session was supposed to be over, but anyway, is expressibility. So why is Julia expressible? And this is one of my favorite features of Julia, meta-programming. What does it mean? So Julia is a homoiconic language, which is just a fancy word to make me sound smart, which basically means that in Julia, you can manipulate a Julia code inside the Julia. What does this whole inception trip mean? It means simply that in Julia, you can easily write programming languages inside the Julia to model specific problems. And this is my favorite example to motivate it. Now, this is from chemistry. We are electrical engineering, but still. So here you have this at reaction network. So this is a macro. And then you write something which looks very much like chemistry reactions. So this is a valid Julia syntax. These arrows and stuff looks like Julia code, but the macro gives different meaning to it. And particularly what it does, it says, okay, now these are the reactions, build the differential equations from this. And now you write these and you get like differential equations of this chemistry reaction and you can solve it. So this is very, very good for modeling with scientists, engineers, because you can write like your language. You can write electrical quantities like electrical quantities. You don't need low-level Fortran C++ functions. very readable, and builds the differential equation for you. Other example that maybe might interest a few more people here. So Marcelo also talked about fuzzy logic in power electronics modeling. So there's this fuzzylogic.gl library, and full disclosure, it's my library, so of course I'm biased, which has this macro, which allows to build a fuzzy inference system by writing this way. So if you have used the MATLAB fuzzy toolbox, you have a bunch of functions you have to manually write, call this variable this way, attach these membership functions, write the rules as a matrix, and so on and so on. This way, I can write my fuzzy system that looks like a function, and this macro under the hood takes this nice looking Julia code and transforms it into the low level Julia code to build the fuzzy system. And it's very expressive. And this is all at compile time, so still fast, because it doesn't affect the runtime. But yeah, I guess I had to have an example about electrical circuits since I'm here. So this is from like modeling toolkit.gl, a library which has a bunch of functionalities for modeling mechanical electrical systems. And so here I'm showing how you would build a simple RC circuit. So you would write like this. You would define a resistor, a capacitor with some parameters. This macro again allows you to write nicely, and then under the hood builds the object to model the resistor with all the equations. You can also touch equations, I think. Yeah, then you write the connections, and then you can simulate the circuit. So to recap, metaprogramming allows to build small programming languages inside Julia, which allows to model your field, electrical circuits, chemical reactions, whatever, in a more expressive way. So write something that looks like your domain, looks like your maths, and let the macro Julia metaprogramming write the low-level ugly Julia code to build the stuff. Last example about this is Jump, this very, very cool library for optimization. So it has, again, macros, which allow to specify optimization problems in a way which looks very much like you would write in a textbook. So if you look at it, you specify the variables, set the constraints that each variable is constrained to be bigger than 0. Then say, okay, I want to minimize a sum. And then you set the constraints that like each row, each variable has to satisfy some constraints. And this looks very much how you would write in a textbook. And the macro makes sure to build for you the low-level code to write it efficiently. So metaprogramming for expressiveness, fast because of multiple dispatch. There's more resources if you want to know more. Composable allows to plug neural networks into differential equations easily. If you have different libraries from different domains, you can plug and play with all of them. It is very good for research. Finally, to conclude, a very short announcements. So if you want to know more about Julia, the coolest event is JuliaCon, conference about Julia every year. This year is going to be in Eindhoven, Netherlands. I'm going there. Actually, I'm in the organizing committee also. From 9th to 12th of July in the big football stadium. So it's going to be cool. Very big event. Best place to stay up to date with Julia news. Second best is, as Marcelo was mentioning, we have this workshop in Vasa, Artificial Intelligence and Machine Learning for Energy Transformation. And inside this workshop, I will give a 3-4 hours hands-on tutorial from zero to hero for Julia for modeling. So we start with Julia overview, how to do and solve optimization problems with Jump, machine learning, and scientific machine learning. From zero to hero with breaks, of course, so that our brains don't become smushy. But if you are interested in what I said here, come to Vasa. It's said to be the most beautiful city in Finland. I don't know if it's true, but said to be, and learn all you need to use Julia in simulations. And finally, also from SIMBA people. If you're interested, it would be cool to chat about how can actually Julia and SIMBA integrate. So thank you for listening. And yeah, if there are any questions, I can answer them.
Thank you very much, Luca. I think we have one question that has not been answered because during the presentation, we received the question, we tried to answer most of them. One of them was, what do you think with meta-heuristic approach for optimization or prediction in this context? I don't know who wants to answer.
I think this was during Marcello's. Sorry?
Meta, I don't know if this meta heuristic is about machine learning or about Julia. I don't know the context.
Like looking at the timestamp, it was asked at 38 past, so it was kind of
It
at
was
the
for
end of your
Marcelo, I
presentation.
think.
I think,
Yes,
yeah.
I think so.
I do not understand exactly what the person wants to ask, but I try to anyway cover what I understand. Okay, meta heuristic would be, for example, trying to understand how a system operates by their functionality. Okay, let's say that you have a wind energy system, and that wind energy system is connected to a converter that's connected to the grid, and you have to supply electrical power, and you have to understand demands. So what would be the meta heuristic? You go a little bit on the top of this layer and try to observe in a comprehensive way. And sometimes we may not have differential equations to describe that, but we have a heuristic, an ad hoc understanding. So I know as the wind will increase up and down, I'm going to have more energy coming up and down, and you'll be, how to say, stored or delivered to the grid. It's very difficult to have all the mathematical formulation for that, but when you talk to people who understand the expertise of that, they will say that, well, maybe the tariff of the connection to the electricity grid is high or low, so I would like to maybe save energy in my battery now because I can sell later in the night or in the day, you know. So this meta heuristic can be taken in consideration in our programming by having what in the past we used to call expert systems. Okay, we can call expert systems, but could be, for example, taking consideration using a fuzzy approach, or maybe taking consideration using some neural networks formulation, when we try to understand the system in a heuristic, in an ad hoc way. I don't know if that was a good answer or not, but that was the way I understood the question. I think you are mute, Frederick. And I think there was a survey at the end, and maybe you can conclude. I don't know, and maybe I can have conclusions. I don't know. Up to you. Go ahead.
Yes, I have just maybe one another last question. How to deal with different time domain simulation in smart grids? For instance, combining controller responses, microseconds, with energy management system decisions every 15 minutes. The question is in the Q&A. If it's too long.
There is a question, 15 minutes. No, I try to answer this in the way that I approach this.
Yes.
See, when I approach this kind of problem, we try to understand what are really fast dynamics versus slow dynamics. And this depends on the problem. For example, if I have a power electronics converter, and the power electronics converter needs to generate pulse width modulation. Pulse width modulation will need a sampling time of 100 microseconds or 50 microseconds, because you have to generate a pulse width for a transistor to turn on and turn off. That's very fast, okay? Compared to, for example, that you are charging a battery. If you are charging a battery, the battery will take hours to charge or discharge. So when I want to simulate charging the battery versus the requirements of the switching of transistors that will turn on and turn off, the converters to control the current that goes into that charging of the battery, I have to have a layer that is how to say, shielded for the fast control, let's say the PWM. And then I have to have another layer, it's a nested layer of another control algorithm that will be running, let's say, every 1 millisecond or 100 milliseconds. How they communicate is a matter of implementation, and that depends if you are doing this in a personal computer or maybe in a digital signal processor. But we can go along techniques of real-time operating systems, where I have interruption every few microseconds, and then I have another another nested activity that will be interrupted, let's say, every 10 milliseconds. So we have to control how the system behaves on that. And when we implement, there are several ways to do it. For example, I just say about your competition, let's say in MATLAB. In MATLAB, you can insulate a block and say that this is running every let's say 100 milliseconds, and this is running every 10 milliseconds. And maybe there is a certain time that I'm available for communication with the external world, okay? So when you implement that and you make in that the design that reflects the dynamics of your system, and at least you understand what's fast versus slow simulation, you are trying to attend to real-time constraints. It's very tricky because nowadays people are not familiar with real time because they believe everything happens at the same time. But this is not true. In a machine, the machine will execute the code sequentially, unless you have a parallel computer, okay? So in the machine, you have this serial execution, and you have to somehow have a multitask and time sharing of that. So this is something that we have to consider in the design, and you have to have simulation tools and techniques that allow us to have this multi-sampling implementation of control systems.
Okay, thank you very much, Marcelo, for your complete answer. I would like to thank everyone also for their patience because we exceeded a little bit the time. Thank you again for attending our webinar. I would like to thank Marcelo, Peyman, and Luca for the great presentations. We had many questions about will the slide be shared and so on. Marcelo, Peyman, and Luca, I think it's not an issue for you to share the slides.
I actually, mine are on my website, so just put the link in the chat actually. I don't know if everyone saw that. It's host and panelists, but maybe it's not for participants.
And I can maybe add that to the email. So you will receive also after this, this webinar an email with the recording of the webinar. And for the presentation, we can send them by email. I will figure out a way to do it. No problem. So thank you again to all of you. We wish you a very good day, and we hope to see you at our next webinars in the next future. Thank you very much. Bye.
Thank you very much, everyone, to this very nice collaboration, this cooperation. It was great. I really appreciate the support of everyone in PowerC, SIMBA, and the group here, especially Luca and Peyman. Thank you. Have a great day.
Thank you very much, Marcelo.
Thank you. Thank you very much.
Thank you,
Have a nice day.
Peyman. Thank you, Luca. Bye-bye.
Thank you.
Bye.